Hello, this is Chapter 7 on Oscillations for Physics 102A. This is the Homework Solutions video. We'll start with number 34, involving electroencephalograms, or EEGs. You can see there's a picture of one down below number 34 on this page. It says they study electrical oscillations in the human brain. Beta oscillations have frequencies from 12 to 30 hertz. What is the corresponding range in period? So just remember that period is the reciprocal of frequency. So 12 hertz, and remember what a hertz is, it's a cycle per second. So the period is the reciprocal of that. It's going to be seconds per cycle. So we'll do 1 over 12, and that'll give us 0.0833 seconds. For the high frequency range, this will be a shorter period. 30 hertz, and we'll do 1 over 30 cycles per second is 0.033 seconds. Number 36, looking at the heart rate, an athlete's heart beats 145 times per minute. Find the period and frequency of the heartbeat. All right, so let's think about the units. It's given as 145 beats per minute. Now, when we talk about frequency or period, we want the timing in seconds. So let's get that in beats per second. Here we have beats per minute, and to turn it to beats per second, we'll put 1 minute over 60 seconds. You can see how the minutes are going to divide out, and we're left with beats per second. So 145 divided by 60 is 2.42 beats per second, or we'll say hertz. And then the period, how much time it is between each heartbeat, is just the reciprocal of that. So 1 over 2.42 is 0.414 seconds. Number 39. A 1.4 gram spider dangles from the end of her silk thread, undergoing vertical oscillations at 1.1 hertz. What's the spring constant of the spider's thread? All right, so we're given mass is 1.4 grams, frequency is 1.1 hertz, and we're going to remember these two equations. We can look at the period or the frequency equation, whichever is most useful to us. So period is 2 pi squared of m over k. If we want frequency, it's just going to be the reciprocal of that, so 1 over 2 pi times squared of k over m. And because frequency is given, this is going to be the more appropriate equation. So we're going to take this equation, the F equation, frequency, and solve it algebraically for k. So we'll multiply both sides of the equation by 2 pi. We'll square both sides, and we'll multiply by m, and that leaves us just with k on one side of the equation, and 2 pi f squared times m. So we get k is 0.0669 newtons per meter. Now, it's good to check because we might have a tendency to mess up on the algebra. So you can check, take that k answer, plug it back into the formula right here, 1 over 2 pi times square root of 0.0669 divided by the mass. Make sure that you have done mass in kilograms. So 1.4 times 10 to the negative 3. And that will give that should give a frequency of 1.1 hertz. Number 40, a bungee jumper undergoes simple harmonic motion with amplitude 5 meters, frequency 0.125 hertz. Graph position versus time for 2 oscillation cycles. All right, so we're going to do a cosine curve here, and we remember how to draw a cosine curve. If we start at time equals 0, we can start, a cosine curve starts up at the amplitude, and notice I've labeled the x-axis 5 meters and negative 5 meters, so that's the amplitude. And a cosine curve will start up at 5, and in one period it'll go down and then come up again. There's one period. And then another period, it'll go down and come up again. That's 2 periods. Now, we need to label the time axis, so we need to know how much is one period. So frequency is 0.125 hertz, period is 1 over frequency, so 8 seconds. So then we can go in afterwards and label our time axis. So at the 1 full period, it's been 8 seconds. We can say at the half period, from the time the bungee jumper went from positive 5 meters to negative 5 meters, that's 4 seconds, and then 12, and after the second period, we have 16 seconds. Now, if you have a graphing calculator, you can do this on the graphing calculator. The graphing calculator is going to want you to plug in a function like you see where my red pointer is, x equals, and we need a cosine curve. And the amplitude's kind of obvious, 5 times cosine of, but then we need to be in radians mode for our calculator, and the bit that's multiplied by t, so the coefficient on t needs to be omega. So we need to figure out what is omega. Omega is 2 pi times frequency, so 2 pi times 0.125, and it gets 0.25 pi. So once we make all those adjustments, we can write this into a graphing calculator, and it should give us this same graph. Now, we need that formula in order to do number 41. So number 41 says, assume the bungee jumper in the preceding problem follows the simple harmonic motion equation x equals a cosine omega t. Find the jumper's position at the following times. Okay, so if you didn't pay attention in the video on number 40, how I got this formula, you need to go back and do that. So even if you don't have a graphing calculator, you need to be able to come up with this equation. Again, the coefficient on t is omega, and so you can go back and see my explanation on number 40, but that's going to be 2 pi times the frequency, 2 pi times f, and there's the formula. So now once we get this, and make sure your calculator is in radians mode to do this, then we just type in the various times, and you should get 4.9 seconds, 0.5 seconds, and 1 second. Number 46. A mass spring system has K equals 110 newtons per meter, mass of 1.45 kilograms. If it's undergoing simple harmonic motion, how much time does it take the mass to go from A to 0? All right, so it's very helpful to graph this. And so let's graph, we'll do a cosine curve. And it starts up at A, and it goes down to 0, then negative A, then 0 and A. And this helps us to see that to go from A to 0, it is 1/4 of the period. So this question is asking, how much is 1/4 of the period? So let's find out what the period is. Period is 2 pi times square root of m over k. We get 0.7214 seconds, and then the quarter of the period is 0.180 seconds. Number 51. You hang a spring vertically from the ceiling and attach a 660-gram mass to the bottom. When the mass is at rest, it stretches the spring a distance d. If you pull the mass down and release so it oscillates with a period of 1.04 seconds, what is d? All right, so let's set this up. Let's have a force diagram here on our mass. Its weight is hanging down, and it says that it has stretched a distance d. So by Hooke's law, the upward force on it, that restoring force of the spring that's trying to bring it back to equilibrium, remember, is k times displacement, so we'll say k times d. Now, let's use F equals ma, where acceleration is 0, because it's just hanging there, not moving. And we can say kd minus mg equals 0. And then we can say that d is equal to mg over k. All right, let's leave that to the side for the moment. We are given information about the period and the mass. So let's see how those relate. We can say period is 2 pi squared of m over k. We can solve for k, and that's 2 pi over t squared times m, going through that algebra. And now, the question was asking what is d? So if you go up here to where my pointer is, there's our equation for d equals mg over k. And now down here in the green, we have an expression for k. So let's take this expression for k and plug it in to this formula. So now come down here, D equals mg over k, and let's plug in the expression for k. K is m times the square of 2 pi over t. And so we've got this big fraction here, mg over m times the square of 2 pi over t. Let's clean this up. And what we can do is get rid of m divides out. It's both in the numerator and the denominator. And if we're dividing by the square of 2 pi over t, let's call that multiplication by the square of t over 2 pi. So here we have that d comes out to be g times the square of t over 2 pi. And we can just plug in all those values. Because we know t, of course we know g, and so we get that d is 0.268 meters. By the way, notice that mass is irrelevant. Number 68, dealing with a pendulum. What is the gravitational acceleration on a planet where the period of a 2.2 meter long pendulum is 2.87 seconds? All right, so we are solving for g. We are not on planet Earth. We're on a planet with some other g. And so we'll use the equation t equals 2 pi times square root of L over g, but we're going to solve that algebraically for g. So we'll divide both sides by 2 pi. We'll square both sides. That leaves us with L over g. And go through the algebra and solve for g. So you should be able to do that. Then once you solve for g, you can plug in all those values. We're given t, we're given the length, and you should get 10.54 meters per second squared. And you should check your work. Take that answer that you think is the value of g, plug it back into the original equation up at the top, and you should get the period that was given in the problem of 2.87 seconds. Number 69. On a swing, a 35-kilogram girl undergoes small amplitude oscillations with period 4.1 seconds. How long are the ropes that support the swing? And how is the period affected if the girl's 48-kilogram brother replaces her? All right, we're going to assume her to be a simple pendulum. Simple pendulum, because that's the only kind of pendulum we're working with. Assuming that the ropes are long enough compared to her size. And we want to solve for length. So period is 2 pi squared of L over g. We're going to algebraically solve this for L. And when you go through a couple lines of algebra, you get that for L. Plug in the values to get 4.17 meters. Then for part B, how's the period affected if her brother, who is a greater mass, replaces her? And you realize as you look at this equation that mass is irrelevant, so there's going to be no change. Number 71, a pendulum makes 25 oscillations in 32 seconds. Find the period and the pendulum's length. All right, so it's giving us the timing a bit awkwardly, but I want you to think about that period is seconds per oscillation. So usually I've said seconds per cycle. And frequency is cycles per second. So when we think of period not merely as seconds, but seconds per cycle, then we're going to set it up that way. So it is 32 seconds per 25 cycles. Just divide them. And that gives you that one cycle is 1.28 seconds. That's the period. If you want to know the frequency, which the problem is not asking for, but you would just take the reciprocal of that. Question B then asks, what is the pendulum's length? Well, in number 69 above, you can see I've algebraically solved for L, so be sure that you can do that. We get L is the square of t over 2 pi times g. So we plug in t, g, do that, and we get a length of 0.407 meters. Number 77. At sea level, g varies from about 9.78 meters per second squared near the equator to 9.83 meters per second squared near the North Pole. Find the difference between the small amplitude periods of a 2-meter long pendulum at these locations. We had a previous problem, problem number 68, I think it was, where we're on a different planet and we have to solve for G. Well, we don't even have to go to another planet. There are slight variations on Earth. So G at the equator and G at the North Pole, they're both about 9.8, but they're a little different. So to approach this problem, let's think about first what it's asking. Find the difference between the periods. So I'll set it up this way. Delta T is T at the equator minus T at the North Pole. And then let's use the equation for periods. So 2 pi times square root of L over G at the equator minus 2 pi times the square root of L over G at the North Pole. Now at this point, you can just plug in all those values. I'm going to algebraically simplify this a bit, but you can just plug in all the values. You might want to factor out 2 pi, but you know the length, 2 meters, the g's that are given, and you can get the answer from here. However, let me get a bit more algebraic. The rest is unnecessary, but I factored out 2 pi and the square root of L, and I'm left with 1 over square root of G at the equator minus 1 over G, or 1 over square root of G at the North Pole, and then I can plug in those values. So 2 pi times the square root of 2 meters times 1 over the square roots of both those numbers, and it's going to be very, very tiny. So what we end up getting is the difference in periods is about 7 milliseconds. So very, very tiny difference because of the difference in gravitational strength. That is the end of the Chapter 7 homework. Have a great day.